Okay, so what should we do today? Half seriously. Okay. Well, actually, that was my first choice. So, yeah, because now, of the 8 people in this class, 3 have now turned in homework 1, and some who I've not, I know, are almost ready to. So, what? Oh no, I brought it with me. Yeah, yeah. I was semi-prepared today. Okay. Homework 2 gets into spectral methods, and also comparison with finite difference methods. So we do some of the same things on homework 2 that you've just done with homework 1. Okay, so as for 2 problems, so we did some number of problems. It's like one homework set spilled out over time. So that's how the MIT site did it. So we have minus epsilon uxx plus ux equal to 1 on minus 1 to 1. Homogeneous Dirichlet boundary conditions, convenient. Okay. And value of epsilon is given 10 to the minus 4. This is an interesting kind of problem because technically it's a second order PDE, but because of a small value of epsilon, you might see behavior that you might expect more from a first order PDE instead. The other point I want to make is, let's suppose that epsilon actually was 0. Then you just have ux is equal to 1. So what function u would, so therefore what form would you have? What kind of function would it be? Yeah, it'd be a linear function. So it would be something in this form, ax plus b. But from the boundary conditions, what would you have to be? What's the only function of this type that also satisfies the boundary conditions? But then ux wouldn't be 1.
So just I know.
So what's the only option left?
A constant.
Which constant? 0. Yeah, you can only get a trivial solution. Okay, but now we have this epsilon minus epsilon uxx term, which allows for a quadratic function. Okay, first we'll talk about how you get an exact solution to compare with, because you have to dust off your 285 knowledge on the last homework set.
Because it's non-homogeneous.
Yeah, that complicates things a little bit. What?
I hate
Oh my God. Okay. I'll get the process started on that. So, all right. So we have our characteristic equation. Like you did in the first homework, so you have minus epsilon r squared plus r is equal to 0. So then your solutions for that would be
just for trivial 1 and then r is equal to 1 over epsilon.
Yes.
Yeah.
So
that's as far as I got.
Oh, okay. Well, let's get already started on that. Okay, so we have 2 distinct real roots. So your homogeneous solution is constant plus a number constant e to the 1 over epsilon x. But now you have this non-homogeneous term of a 1. Now, I don't remember the names of the two methods that are taught in the, like in 2 and 5.
Variation of parameters and something about coefficients.
Method of undetermined coefficients.
Yeah. Sure.
Yeah. So, if we take a look at undetermined coefficients, just because I don't feel like repeating a Wronskian, that the form of your solution, I'll call it UP of x. So normally, since we have a constant over here, you might think, okay, there's going to be a constant, which I'll call A. But the fact that, I remember Dr. Chen always referred to this as conflicts, or I would call it overlap. Like this one, the constant, would arise from the root of your characteristic equation being 0. So basically you get whatever root is associated with your non-homogeneous term. And yeah, that 0 overlaps with the roots here. And what that means is you have to include an extra factor of x. So your non-homogeneous solution is of that form. So then you have to substitute that into the PDE. But well, actually, if you go ahead and substitute that in, what are you going to get? So you just take this and substitute that in there. So what would you get for A?
A equals 1?
Yeah, A equals 1, because you plug it in and you get second derivative would be 0, first derivative would be A. So A has to equal 1. So your non-homogeneous solution is equal to x. Therefore, your whole solution, u of x, is constant. So actually what happens is you get a linear function, but happens to have slope 1. And then because of the only influence that the epsilon has is this exponential term, 1 over epsilon x. And then the coefficients C1 and C2 have to be determined by the boundary conditions. So then you'd have a system of two equations to solve from that. Actually, yeah, it'd be kind of messy analytically. If you want, you can set up a system in MATLAB and work it out.
Why x has no coefficient?
Yeah, a particular solution never has an unknown coefficient. Yeah, you just because you're finding a solution. And your solution space tells dimension 2. Okay, so you have something of that form, and actually at this point I would turn to MATLAB to give you the values of C1 and C2 by filling in the given value of epsilon. Okay, so at least you have a exact solution to compare against. So epsilon, so it's the e to the 1 over epsilon x. Since epsilon is small, this is going to be like super large, or it can grow very, very quickly. All right, I gotta know. So u of minus 1 is going to be c1 minus 1 plus c2 e to the minus 1 over epsilon, and that has to be 0. And then u of 1 is c1 plus 1 plus c2 e to the 1 over epsilon, and that also has to be 0. So then if you write this in matrix vector form, okay, so the constant terms, I'll just move to the other side. So I'm going to have 1 and minus 1. And then the coefficient of C1 in both cases will be 1. And then the other coefficients will be e to the minus 1 over epsilon and e to the plus So
Do you want me to set it up and set it real fast?
well, I have MATLAB open, so
Okay.
okay. So epsilon is 10 to the minus 4.
Yeah, I'm trying to work it out by hand. It sucks.
Yes, it does.
So.
Yeah. Oh, that's a problem.
What?
I put it to MATLAB, and it says calls this entry calls it infinity.
Oh.
Okay. Okay. Let's see if we can resolve this somehow. We'll see. Even if information is not computable, if we work it out analytically, maybe the final result could be something that can put in MATLAB. Okay. So, these are two possible problems with floating point arithmetic, the big ones. We've come across catastrophic cancellation before, but now we have overflow. We're talking like e to the 10,000. So, okay. So the solution is equal to so the inverse of this. So we have e to the 1 over epsilon minus e to the minus 1 over epsilon times. So we swap the diagonal entries and then negate the off-diagonal entries, multiplied by the right-hand side. So what we get is, okay. So I'll just separate them. I need to make sure I'm getting all this. Okay, so the first value for C1, I'll just write here. So it'll be e to the 1 over epsilon minus e to the minus 1 over epsilon over, plus.
I have C2.
Okay. And what do you have for C2?
2 over e to the minus 1 over epsilon minus e to the 1 over epsilon.
Okay, yeah.
And then C1 is just...
It's 2 over e to the minus?
Yeah, e to the minus is first.
Okay, yeah. Okay.
Oh, wait, no.
Well, yeah,
yeah, I'm right.
Yeah, minus 2 at first. Yeah, okay. Well, not sure how much this helps, but
I did that, differently. I was using the matrix.
Oh, okay. So the thing is, that would be, okay. I'm not sure really either one of these could be readily computed, just because, this one, e to the minus 1 over epsilon is so tiny that from a floating point derivative point of view, the first element would basically be 1. The second element would essentially be 0. In other words, that exponential term just wouldn't be there, which makes sense because for positive x, you can have such exponential growth. You would want that constant to be really small. Well, that's an interesting problem. Now,
So is it just so jacked up, and that's why spectral methods is going to work better?
I guess we'll find out, won't we?
Okay.
Because it says, again, this is straight from the MIT problem, implement a simple finite difference method and run an error analysis. And they didn't really elaborate on what that meant. What I would do, since an exact solution is not viable to compute, so we'll just forget that. That was fun. So glad we looked at that.
So don't do A?
Don't. No. don't compute an exact solution. Okay. What I would do with an exact solution not available, what I would do is go ahead and implement finite difference method like you did in. Okay, let's talk about the numerical. Okay, I accidentally stopped recording, but now we're. So in finite difference code, what's going to happen is you're going to set up a system solve similar to what you had before, but now, in the first homework, you were solving problems on interval 0 to 1. Here it's -1 to 1, so your h is going to be like 2 over n plus 1, rather than 1 over n plus 1, because interval with 2. You're still going to have Dirichlet boundary conditions, so you're still going to be solving for the interior point. So that part is no different than the previous problem. And then your system to solve, right, is like AU is equal to F. Well, your F is easy, that's just a vector of 1s. And A is going to be the minus epsilon times same kind of second derivative matrix as before. Let's do a second order method, nothing fancy like in the first homework. Plus a first derivative matrix. Now, you have some choice here, and it might be interesting to see if there's any substantial difference in behavior. Like what you can do is it's using a center difference for a first derivative. Or seeing if there's any difference in behavior if you use like a forward difference or a backward difference. But I'm thinking center difference just because of greater accuracy. And see what happens. Also see what happens for different values of h. Because so what's going to happen is because this term is going to be, well, on the one hand, epsilon is going to be small, but 1 over h squared is going to be pretty large. Yeah, I'm curious. I'll be curious. I've not tried to solve myself yet. I feel like something's going to go wrong, and we'll have to see what that is.
So like, to compare to like an exact solution, doesn't MATLAB just have like a built-in ODE solver?
Yeah, they do.
Would that be appropriate to use to like try to just be like, all right, is my solution anywhere near the exact solution?
Yeah. Well, let's take some time to talk about that too.
Okay.
Well. Yes, it's got to be a very different approach than doing this. But well, before I talk about that, I want to. Okay, so that's part A. Just try it out, see what happens. For different values of h. And one thing that I've done in problems where I don't have an exact solution. This is for like time-dependent problems, but it's the same idea for a time-independent problem. If I compute the solution for several values of h in this case, then the one with the smallest h, if I'm observing convergence at all, I can think of the solution I compute of the smallest h as being kind of like the exact solution. And therefore, I could compare my other solutions to it to get an idea of convergence. Is it second order accurate? So that's one thing you could try. Now, what complicates matters here, though, is if you compute solutions with different values of h and you want to compare them to each other, then the trouble is they're evaluated at different grid points. All right. So So here's what you could do, for instance. Let's suppose I compute solutions for two different values of h. Okay. And actually, yes, so my way to do this would be creating solutions of different grids. But you have to interpolate. You have to select certain points. So I want, if I choose a certain spacing h, and so for example, I'm going to say, for this, as an example, let's say n is equal to 99. So h is going to be 1 over 100. Then I compute another solution where n is equal to 199. So h is equal to 1 over 200. So it's exactly, make sure it's exactly half. Okay, my hash marks are all off here. This is disgraceful. Okay. So then you go ahead and compute your two solutions, and you select every other point. So if you have your vector, I'll call this u1 is your computed solution for this case, and then we have u2 for the other case. So you compare u1 to, well, you want the points, like for the finer solution, you want elements 2, 4, 6, because it starts here. This is u1 of 1. This is u2 of 1, u2 of 2, and so on. Because it's the solution that you compute has only the interior points included. So I compare u1 against u2, and you can do this: 2 colon 2 colon n, for instance. So that selects every other point, starting with the second point. So you can use that to judge error. Now, to judge order of accuracy, you actually need to compare at least 3 solutions, because you want to see what, because 3 solutions will give you 2 errors, and you can see the trend. And how's the error going to 0 as h goes to 0? If error is going to 0. So I can do another, like with n equal 399. So h is 1 over 400, and I would take like every 4th value. So I could do like u3, 4 colon 4 colon n.
So are we using h is 1 over n plus 1 or 2 over n plus 1?
Ah, dang it. 2. Okay. Same idea. Okay. Yeah. So you just make sure that your denominator keeps doubling. Just so h just keeps getting cut in half. Okay. All right, so that would be one way that without an exact solution, you could still try to gauge order of accuracy.
Why do you have the second, the 1 over 2 h? The second matrix?
Because of first derivative. Yeah. Yeah, that never came up in the first homework set because you only had one derivative term in your PDE. Okay. All right. Are any questions about that part before I talk about, well, Haley's idea of using an ODE solver to get an exact solution?
And then how to choose like which ODE? ODE, like I know that ODE that there should be something after that.
Oh, like which ODE solver?
Yes, I mean how to choose which one.
Well, most of the ODEs I solve are stiff, so I just choose ODE 15s. It seems to be the best one, especially for small problems. I mean, ODE 15s can be expensive compared to other methods, but for something like on a homework, it's might as well use the best tool. Okay. So if I want to express this as an ODE form, actually, that's going to be a huge pain. Here's,
Okay. Maybe I won't.
but I'll explain why. Because of boundary conditions. I could describe this like, okay, I'm solving for, I can think of x as t. So I'm solving a problem on t going from -1 to 1. And I can say, well, this boundary condition would be like an initial condition. And that's fine. I could describe the PDE as a system of two first-order ODEs. So that's no problem either. But how do you know? But the trouble is you have to specify a slope. I need u prime of -1, and I don't have that. So does anyone remember from, well, actually, I think the only class I've taught this in is 561. When you have a problem like that, where you have a boundary value problem, but you want to describe it as an initial value problem, and you have to guess the slope at your left boundary to hit the value at the right boundary, what method does that?
Say that again.
So you solve a boundary value problem by thinking of it as an initial value problem. You guess a slope, and then you try solving it as an initial value problem and see if you hit the correct value at the other end. It's in your right boundary condition. And if you don't, then you have to adjust it and try again.
What does it start with?
S.
A
Shooting method.
I was like, projection!
I was going to say
Well, then why didn't you?
that.
Yeah.
When you said S, I was like, yes, I can say this.
Should I do that more often? Yeah. This is like math by Wheel of Fortune. But can I buy a vowel? Okay, so, but you have to implement a shooting method, and it's like, no. So we're doing this without an exact solution. It'd be different if epsilon wasn't so dang small. Then e to the 1 over epsilon would be computable. Well, if I chose, instead of 10 to the -4, like 10 to the -2, so let's say e is 10 to the -2, and I compute the matrix again. Well, what you have is the 2-2 entry of this matrix is 2.7 times 10 to the 43. So well within representable numbers, but still pretty dang big. Okay, so that makes things more interesting. Okay, now, as far as the part of the problem that this assignment is actually about, spectral methods, here's how that would go. Okay, so part B, using Chebyshev points, xj is equal to cosine of pi j over n. Now j going from 0 to n, so n plus 1 points altogether, actually, well, all right. I will stick with the same notation that's used in the note. So that includes the boundary points, but you really need to solve a solution at these interior points, n minus 1 of them, because you know what the solution is at the boundary. So the system you're going to solve, and there are examples in the notes that were like this. So you're going to solve minus epsilon. Wait, was it minus?
Yeah.
Yeah, minus epsilon d. Oh, use an uppercase n. I think it's what I was doing in the notes. dn tilde squared, your second derivative, plus dn tilde times u is equal to f. Now f is still just going to be a vector of 1s. And so dn tilde is the interior part of that Chebyshev differentiation matrix. And as far as setting up that matrix, well, once you set up the first one, yeah, then you literally just go ahead and square it. to get the one for the second derivative. So it's getting that first derivative matrix. That's a pain. And as far as the best way to do that, because it's kind of tedious. Okay, I'm just going to look up at my earlier notes. Because on one hand, there are formulas given for the entries of D. And what you would do is you would ignore the first and last rows and columns. So a lot of the special cases you could just forget about. Well, I'm going to describe two ways to get the matrix, and you can do what you're looking for. I really don't care. Okay. So getting D and tilde. So approach one, just using the direct formulas in the notes, that would be, so this is for I and j equal 1, 2, up to n minus 1. This is going to be n minus 1 by n minus 1 matrix. So a more direct approach, using the formulas that have been worked out, d and tilde.
Wait, should it be n minus 1 by n minus 1 or n minus 2 by n minus 2?
No.
That we're ignoring both boundaries.
Yeah, but you have n plus 1 points to start with.
Oh.
0 to n.
0. Cool. Okay.
All right, so your diagonal entries are going to be, so minus xj over 2 times 1 minus xj squared, where this is xj, so you're just going to use that throughout. So you might as well define that vector at the beginning. For j equals 1, 2, up to n minus 1. And then the off-diagonal entries are going to be, okay, so actually this is not pain after all, because you're cutting off those boundary columns. Minus 1 to the I plus j over x I minus xj. Yeah. Okay.
Are you looking at page 25?
Probably. Yes. Okay. Yeah. So page 25 in the notes for I j equal 2 up to n minus 1. The other approach is using formulas up above that are really more general than this. So they're not just Chebyshev points, but any selection of points using Lagrange approach, like basically the derivatives of Lagrange polynomials. So you define these constants first. Aj is a product. K equals 0 to n. K not equal to j of xj minus xk. And then once you have those, then the entries are pretty easy to get. So tilde ij is equal to, so for the off-diagonal entries, it's just ai over aj, xi minus xj. So in fact what happens is ai over aj turns out to be minus 1 to the I plus j. This is off-diagonal. And then for the diagonal entries, that's the sum k equals 0 to n. Again, k not equal to j, 1 over x j minus xk. Okay. Well, it turns out this way it's really not not really a pain after all. It kind of would be more of a pain if you had to include the boundary columns, but at least in this case you don't. Okay, so this is for the diagonal entries. So either way, that's your matrix. So you want to do the same thing where you solve this system for different values of n and see what happens to the error. See if you notice any difference in behavior compared to a finite difference case.
Is there one advantage to using the first method versus the second?
This versus this? Well, in this case, I would go with this one, just because it's actually formula simple to compute. This is what you'd have to use if you were not using Chebyshev points, but some other selection of points. So what I'm hoping is that for this problem, the coding tasks are somewhat simpler than what you had to do in the last assignment, because at least now that you've gotten your feet wet doing certain essential tasks. Now, the other problem in this set, entirely different, still spectral, but you're dealing with a periodic problem, so using a Fourier series approximation. Okay, now, all right, well, okay, for first parts, you're actually not given an F. So, well, okay, part A is you're not coding anyway. So this is about existence of a solution that basically you can't choose just any old F. And the thing to keep in mind is if you have a function that is 2 pi periodic, think in terms of like sine or cosine. What can you say about derivatives? Okay.
They exist. I mean, like, I don't know.
That's a starting point anyway. Not much of one, but okay. All right.
Oh, okay. No, I see what you mean. Sorry.
Yeah. Okay. And this. It's kind of similar to what has come up with, I discussed with case of Neumann boundary conditions in general, like for instance for Poisson's equation, which this is, where a certain condition had to be satisfied for a solution to exist. It's kind of along those lines. So then you have a way of describing all possible solutions, and so that's why the rest of the problem deals with solution with zero mean. Because what happens is, if a solution exists at all, you actually have infinitely many solutions. So how do you pick out the right one? But using Fourier series will have the effect of naturally computing a solution that has a zero mean. Actually, I did an example not too long ago. Would have been like maybe Thursday or Friday of last week, where I was solving 2D Poisson's equation, where using a Fourier series, where you just get the Fourier coefficients of solution very easily just by dividing, but it required that like the 0, 0 coefficient of f hat had to be 0, and as long as it was, then you had infinite solutions. It's exactly that situation again, only 1D. Okay, so so for part B, second order accurate finite difference code. Okay, there's something here I need to talk about that hasn't come up previously. Alright, so this is problem 5B. So you're solving minus uxx is equal to x, f, but u is periodic. So now for finite difference, you're actually solving for one boundary point in all the interior points. So you have, we'll say, u0, x0, x1, x2, up to xn. You're solving on the interval 0 to 2 pi. So xn is 2 pi, x0 is 0. Your h is going to be 2 pi over n. And what you're going to do is you're going to solve for all the interior points in either boundary point. For instance, just for convenience of numbering, you can solve for a value solution at x1, x2, and xn, knowing that the value at this point is going to equal the value at this point. Okay. Now, when you set up your matrix for finite difference, it's a little different from before, because what happens is, minus uxx at a given point xi is going to be minus 1 over h squared. So your same old center difference. Okay. So how the boundary handle is going to be a little different, because, for instance, when let's suppose we have minus uxx at x1. So now I have u of x0 minus 2u of x1 plus u of x2. Well, okay, sorry, this is an approximation. This also is an approximation. And I just use my unknowns for shorthand. u0 minus 2u1 plus u2. But because of periodicity, u0 is the same as un. So there's a wraparound effect going on. And at the other boundary, minus uxx at xn, that'll be un minus 1 minus 2un plus un plus 1, which is off your grid. So that gets replaced with u1. So un is the same as u0. Un plus 1 is the same as u1. So you have that wraparound going in both directions. Now, so here's what happens if you describe this in matrix form. So your second derivative matrix, which I'll call D2, is 1 over h squared. I'm just doing the second derivative, so that's why I don't have a minus. But you have to remember to put a minus at the end. I've gone on record saying that, okay? Yeah. So don't forget to take minus. Just second derivative, you have the same pattern as before, minus 2 down diagonal, 1s down in super diagonal, subdiagonal. All that's the same, but how do you take a wraparound into account? what else do I need to put in here now, but I didn't have to before? Yeah. So for this one, I need a UN, so I needed 1 in the last position in the first row. And then here, UN plus 1 wraps around to U1, so I had to put 1 in the first position there. So this is called actually, who knows what it's called? What kind of matrix? Yeah. I sense some familiarity. Yeah, this is a circulant matrix. Circulant. Okay. So when you're dealing with periodic boundary conditions in general, you have this kind of wraparound. Okay.
So we have circulant matrix just because we have periodic boundary conditions.
Yes. Okay. Now, so you might think, okay, for this part of a problem, no big deal. I set up a matrix, and then you go to solve. Minus d2 u is equal to f, where f is just the values of your function f of x at the grid points, x1 to xn. But there's a huge problem. What?
No, go ahead.
D2 is singular. It's determinant to 0. Now, this is fixable though, because first of all, if you do backslash, and the system cannot be solved, it will try to solve it in a least square sense. So what you can do is, so in a least square sense, you're actually solving this problem exactly. Minus d2u is equal to pf, where p is the projection of f onto the range of d2. So you have to make sure, the thing is, to keep in mind is, any system of equations whatsoever, doesn't matter if it's invertible or not, or even if it's square or not, any system of equations whatsoever of any kind can be solved if, or it has an exact solution if and only if the right-hand side vector is in the range of a matrix. No matter how restricted that range can be, if it's in the range, a solution exists, period. So you just have to make sure of it. And that's actually what's important about the part A, ensuring that a solution exists in the first place. You're not going to choose any old f. You have to choose f that satisfies this compatibility condition, and then it will naturally fall within the range of the matrix. Therefore, a solution can still be found. I'm pretty sure that backslash will still work under both circumstances, because it's, and I may give you like a warning or something saying this matrix is singular, but a least square solution definitely exists. Because I can actually tell you the null space of this matrix, because if you look at every row has the same elements, just in different positions. The sum of all the elements in each row is 0. So this matrix times the vector of all ones is 0. So when the row sums are equal to 0, that's the same thing as saying that the matrix times the vector of all ones, because the result of this is the vector of row sums is going to be 0. So that's your null space. So what do you have to make sure of, because the matrix is symmetric, and I should add, those of you who took 610 last semester, the problem that I cut out of the homework about dealing with a singular matrix, that's actually what this is about. that if you make sure that f does not have a component in this direction, then the system will have a solution. But the thing is, if you are making sure that f is the kind of f that will, for which the PDE has a solution, this will take care of itself. So in other words, this component automatically will be excluded. So by finite difference methods, it is still solvable. Okay, so this one of the difficulties of circular matrices is the fact that they're singular. Whereas, because if you look at the eigenvalues of the circulant matrix as opposed to the matrix we've been dealing with that doesn't have these corner entries, the eigenvalues behave very similarly. It's just that in the case with Dirichlet boundary conditions, you don't have a zero eigenvalue, whereas here you do. All right, I'll take a break at this point. When we come back, I will talk about how we can solve this problem using a Fourier spectral method as opposed to Chebyshev. Okay, well, so we have a half hour left, so I have a little more to talk about with this set. So I figure, besides doing that and any other questions, I'll probably just be able to elaborate more about this and not actually get into new material because I don't feel like it. So, I can see getting into that new stuff like starting tomorrow. Well, I guess it all depends on how things go up more too. The next stuff on tap is linear systems, direct area methods, and multigrid. Okay. So for problem 5, part C, and then this will segue to part D. So solving Poisson's equation on the interval 0 to 2 pi periodic. Fourier spectral method. Okay. So I can discuss various approaches that you could take. Need to backtrack through the notes here. Okay, so what we'll be doing is solving the equation dn squared u is equal to f. I've used this notation for the Chebyshev problem. Now it's the Fourier version, where the formulas for this matrix are given on page 24 of the notes. And okay. Although, so the way it works is the matrix is described in terms of diagonals. Ij is equal to, the first on the diagonal, you have minus pi squared over 3h minus 1/6 if I is equal to j. And then for the off-diagonal entries, you have this matrix is symmetric. It's Okay. Minus 1 to the I minus j over 2 times cosecant squared of I minus j h over 2. Okay. Now, the only thing that is bothering me about this, and I suppose I could look at Trefethen's text, because of periodic boundary conditions, what we would normally expect is that the matrix would still be circulant. The difference is, whereas in the finite difference case, it's a very sparse matrix. It's tridiagonal plus these two corner entries to make it circulant. Whereas this matrix dn squared would be a full matrix, pretty much every entry non-zero. So, because I want to be able to give clear indication as to whether you just go ahead and use this formula to fill all the, because basically what happens is all the diagonals, along each diagonal you have the same value, just like for a finite difference matrix. But would that naturally lead to a circulant matrix or not? So, like for example, if we look at the finite difference matrix again, over here, the reason that this 1 is here is because of these entries. These entries wrap around to produce this here. These entries wrap around to produce this one here. So if I consider a case where I minus j is equal to 1, like to produce the, like I minus j is equal to 1 would give me the subdiagonal. So would that naturally produce like a corner entry that would happen to be the same? So in other words, is minus 1/2 cosecant squared h over 2 the entry that you would get for the I minus j is equal to 1 case, equal to the entry that would be like in the 1n position. So I is equal to 1 and j is equal to n. So minus 1 to the 1 minus n over 2 cosecant squared 1 minus n h over 2. So first of all, absolutely not if n is odd, because you need this to be negative. The only way this is going to be negative is if n is even. And if we assume that it is, cosecant is 1 over sine. So what we're looking at is, we keep in mind that h is equal to 2 pi n, 2 pi over n rather. So if I look at this expression, 1 minus n h over 2, that would be the same as h over 2 minus nh over 2. nh is equal to 2 pi. So it's h over 2 minus pi. So so then what we're looking at is, if we just look at 1 over this, sine squared h over 2 equal to sine squared h over 2 minus pi. Well, some of you have taught trig. What do you think the answer is?
The answer for
This question.
Oh, minus pi. I should know this.
you're asking about the power of that parenthesis?
Wait.
Yeah, it's the same.
Yeah, they are the same. What was your question?
But well, I asked the question that you asked. Is it about the power of that parenthesis?
Power? What would be the squaring?
Yeah, I mean, I'm told that those are question marks there.
Oh, no.
Just a regular question.
Is this equal to?
Okay.
Yeah,
sure.
yeah. Question mark is not part of a mathematical expression. I'm just asking a question. Yeah, because sine of h over 2 minus pi, if I have a sum difference formula for sine, is sine h over 2 cosine pi, which is minus 1, minus cosine h over 2 sine pi, which is 0. So these are plus or minus each other, but they're squared. About one thing I want to check on in the notes is, when I was deriving those formulas in the first place, I was assuming n was even. Okay, there you go, then. So for this problem, we have to assume that n is even. Otherwise, these formulas would have to be adjusted. So in fact, because of the symmetries associated with sine and therefore cosecant, we really do get a circulant matrix. So that works out nicely.
So if n is even, it is circular.
Yes. Well, if n was not even, the n was odd, these formulas would no longer apply. But whatever formulas you get would still produce a circulant matrix. Because when it's periodic boundary conditions, you get a circulant matrix no matter what. And it's easier to see in the finite difference case. Okay. So yeah, you go ahead and form that matrix. You could, like using, this would be a full matrix, so there's no point using the sparse matrix functions. That reminds me. I guess all of you, I guess probably because I suggested we're using SP diags. Okay. Because one thing that'd be interesting is if you had made a change to your code where the only change is you would form the matrix using full matrix functions, like using diag instead of SP diags. It'd be interesting to see what the difference is in speed. And something for you to keep in mind, and I think this comes up in a later homework problem, timing in MATLAB. If you do tick, and then whatever operation you perform, and then talk, then that will print out for you the time. Actually, don't do it all to prompt, because the time it takes to type these things would be included. So put this in your script to do these statements. So I do this for papers. That's the paper we're working on now to test the execution time. But you can also see there's an option like run and time that will run your code. Like if you run it from within a script, and it'll break down the runtime, like what functions took the most time. And I've used that in some cases to see if I want to make my code faster, where should I focus my energies? What's really taking up the time? And that's helped in some cases. So, but yeah, as you can see, if you try this with your code as it is now, but then working with a full matrix instead, like how much slower it is, especially the solving the system part. You just put tick-tock statements around that and see the difference. It's still going to be pretty fast in any case, because in your case, you're doing like 100, 200, 400 grid points, so not a huge burden on MATLAB, but it'd still be different. But in the spectral case, you're not going to get a full matrix. It's a sparse matrix. It's going to be a full matrix. Okay. So you just go ahead and solve the system using that matrix to see, and you can try this with different values of n to see how the error is behaving. You can do the same thing as I mentioned earlier with different grid spacings, like with h over 2, h over 4, and then pick like every other point or every fourth point to judge accuracy if you don't have an exact solution. Although, for the problems given in part D, you actually can get an exact solution. Certainly for the first one you can. For the other one, that's something that would be a bit of a pain. Well, you can... okay, so part D... All right, first, any questions about this? Now, I do want to talk about another way to solve this problem. Okay. Using, or at least another way to make the matrix. Or it could be a way to solve a problem. Because you're just using MATLAB's FMT functions. Because this matrix Dn we actually know it's eigenvalues and eigenvectors. So it has a factorization of let's see, F inverse lambda f, where the matrix F, entry ij, is just going to be e to the minus I. I have to be careful about this. I'm going to call this omega j. Okay. Each one's an inner product of a certain omega. Okay, so actually omega of... I need to use different letters here, because here I means square root minus 1, imaginary unit. So I can use k for my row and j for my column as usual. So omega of k xj, but xj, we know what that is. And that's 2 pi j over n. And I need to describe what omega of k is. You can think of omega of k as a correspondence which maps all the values from 1, 2 to n to the frequency values. So the actual frequency values are 0, 1, 2, up to n over 2. We're still assuming n is even. And then we have minus n over 2 plus 1 up to minus 1. Actually, the easiest way to describe it would be kind of like basically there's a shift involved. And there'd also be a mod involved to make sure the values go from minus n over 2 plus 1 to n over 2. So, and what happens is these frequencies are ordered in this way because that's what FFT gives you. If you give a function represented as a vector, like a vector f with values at the grid points, and you pass it to FFT, it will give you Fourier series coefficients like fk hat in this order associated with those frequencies. Lambda is a diagonal matrix where the diagonal entries are I times omega of k. K equals 1 to n. So it says these are the eigenvalues of differentiation for periodic functions, all along a diagonal. And then finally, I can write down a formula for the inverse. F inverse kj. Actually, I'll write as jk is it's just 1 over n e to the I omega of k xj. So this matrix F is almost orthogonal. It's just off by a scaling factor. The rows and columns are orthogonal to each other, they're just not orthonormal. So this scaling factor 1 over n is needed to normalize things. So, so the matrix has this nice structure, but you would never have to form a matrix F. So, given a vector U, to get, I know I'm going to regret this, but I'll just enjoy your snickering, to compute the matrix vector product FU, you just perform FFT of U. And F inverse V would be inverse FFT of V. So that's how you go back and forth. You don't have to form a matrix to do a matrix vector multiplication. This will use FFT to carry out the same operation. So, but the thing is, you want to solve a system involving dn squared. So your solution U is dn squared inverse applied to F. But that's the same as F inverse lambda to the minus 2 matrix F vector F. So, so now I can describe in code how you would actually carry this out. All right, so breaking the wall between the boards here. So you let so I'm going to let G be equal to FFT of F, and then you divide each entry of G, so GK by, well, in this case, it's omega of K squared. So it's squared because it's second derivative. We're dividing because we're inverting. Also, normally you might think, if it's this and we're squaring, why isn't it minus omega of K squared? Because there's a minus in the PDE. It's minus UXX is equal to F, so that minus cancels out. And then your solution is just the inverse fast Fourier transform of that. And you're done. You have your solution. So, so these systems are really incredibly easy to solve if you just use the FFT. You don't have to use backslash at all. Your real inversion happens here, but you're inverting a diagonal matrix. So I was like, whoop-de-doo. Okay, so that's the easiest way to, and really the most efficient. to solve this problem using a Fourier spectral method, and that's why these methods are so great for certain problems. Okay. So any questions about the solution process in that case? Good opportunity to get acquainted with these MATLAB FFT functions. So it'd be a good idea to just define this vector up front, and then you have it handy for whatever you need to do. If I had time, what I would be interested in doing is actually carrying out this matrix vector product, on the board, each entry of this matrix, as I know what all the entries are, and seeing if I really do get the entries of dn that are in the notes, like using cotangent and all that. And it also work out that way, at least if n is even. But for now, we'll just take the word for it. that it should work out that way. Okay. Now, for during the last few minutes, I want to talk about part D of this problem. Yeah, so that's way more efficient than it's forming that matrix with all those cosecant squared entries in it. So in part D, you're solving it with for a couple of choices of f. So f is first time sine x plus 5 sine 18x plus 5 sine 20x. So it's pretty oscillatory. So in this case, integrating to get a periodic function is going to be particularly easy because you're just going to take the coefficients of sine and you're going to divide by its square. So you're just going to get sine x again here, and then you have 5 over 324 sine 18x plus 5 over 400 sine 20x. 324 is 18 squared. Because then if you take the second derivative of this, you would get the 20 squared multiplied out here, 18 squared multiplied out here to cancel, and then you have a minus, but the PDE has a minus in it, so that's what the exact solution is in this case. Whereas for part 2, you have a piecewise function. I'm going to write it a little differently than in the problem. So it's equal to minus 1 for x. So x greater than 0, less than or equal to pi over 2. Then in the middle of the interval, so pi over 2 to 3 pi over 2 jumps up to 1, and then it goes back down to minus 1. And the reason for that is, well, it's defined this way. It's not like it's kind of reminiscent of a problem of our first homework where you have a piecewise defined function, but that was at 1 and then 0. Here we go from minus 1 up to 1, back down to minus 1 to make it 2 pi periodic. So what you'd want to do is, like before, integrate this, in which case the u of x would be so minus x squared over 2 plus a constant times x plus another constant, and then x squared over 2. So we have 6 constants altogether. Whoops. C3, C4. Okay. Well, on the definition of these same intervals, So what you want to make sure of is first continuity. You need a periodicity is what I really mean. You want to make sure that its function is 2 pi periodic, and also that its first derivative is 2 pi periodic. Second derivative automatically is because it ends at -1 and loops back around to -1. So you need to make sure u of 0 equals u of 2 pi, u prime of 0 equals u prime of 2 pi. And then if you also require that u of x and its first derivative are continuous at the interfaces, so at pi over 2 and 3 pi over 2, that would give you 4 more conditions, so 2 for u and 2 for u prime, that would specify all 6, so all 6 coefficients would be uniquely determined. So what you could do is you could evaluate so u of 0, u prime of 0, so really u and u prime at, let's see, yes, 0 to pi, and then the breaks here, like a pi over 2 and 3 pi over 2, and have a system of 6 linear equations for C1 through C6. And use those to, and then it's like, and this you're doing some code, not on paper. It'd be kind of a pain on paper, I think, to determine your exact solution for comparison purposes. Okay. One thing that just occurred to me that's kind of unfortunate is, like, MATLAB has format rat to express values as fractions. It's too bad that we don't also have the ability to express values in MATLAB as, for instance, if it's some like multiple of pi, which would undoubtedly happen in this case because we're plugging in multiples of pi in here. It'd be a cool thing to try to implement, but yeah, like, format pi.
And symbolic.
Symbolically, yeah. Whether you're using MATLAB symbolic package or some other tool like Maple or Mathematica that does everything symbolically. Yeah, that'd be a good way to do it too. So, okay, out of time, but I'm sure we'll